Okay, so why do we care? As I'm sure all of you are aware, galaxies are generally residing in dark matter halos, and they're also the sort of the key link between understanding a lot of cosmology and what we observe in the universe, since dark matter isn't observable, unfortunately, much as us theorists wish it were. And essentially, you need to understand the galaxy formation physics in order to understand the cosmology, but to run it backwards, you need to understand the dark matter halos and the cosmology to try and understand the galaxy formation that you care about. And in the long run, this is, and also for the data we currently have, this is relevant to large area galaxy surveys, particularly since we're using the galaxies as the probe of cosmology. For instance, if you want to infer the clustering of dark matter from your observed galaxies, you better understand how the galaxies are associated with the dark matter that you care about. Okay, so what we're doing is using the Bolshoi simulation you've heard a little bit about already, and we're essentially going to be using abundance matching to populate the simulation with galaxies, even though we've heard some words earlier on about how maybe you should be not using pure n-body dark matter simulations. It turns out, for the case that we're looking at, this actually works really well, is what it boils down to. We test our assumptions using some Sloan data from the local universe. It actually ends up being very accurate, and we constrain the grand total of 2 parameters that we use for our model, in contrast to a lot of other more complicated cases. So this is the data that we care about. So we're using the Sloan as drawn from the NYU value-added galaxy catalogs. So this has, for instance, all the nice stellar mass data we use. We're using a volume-limited catalog down to a stellar mass of about 10 to the 9.8. So out to a redshift of 0.06. So that's the volume we have. And that's our sky coverage, which is roughly a third the volume of the simulation we're using. So this is just the dark matter. Okay, so this is the Bolshoi simulation, a high resolution. It's actually very important, in particular, as you've heard about from other speakers, to resolve the substructure. So that's why we need Bolshoi in particular. Okay. So fundamentally, the question is, where are the galaxies? You don't just drop them haphazardly in your volume. They are associated with the dark matter halos. So what we're using is sub-halo abundance matching, called sort of sham colloquially. If you want to think about it like a pillow sham, you sort of throw on top of your underlying n-body simulation, that works. Essentially, you end up avoiding the more complex assumptions of a lot of other models. We're not doing any of these. We're not worrying about how you detail the star formation and feedback, for instance. Our baseline assumption is just galaxies live in dark matter halos. Done. And the galaxy properties have to depend on the properties of the dark matter halos, since that's the baseline input that we're using. So this has been studied previously before numerous times. This is an earlier study, which is just showing, again, in the points here are some somewhat less precise measurements of the 2-point correlation function, and the solid line that passes through them is just an abundance matching result. So this is the sort of thing we're looking to reproduce, but with much better data and tighter constraints. Okay, so this is what I'm talking about. We stick the galaxies in the subhalos, and as well as the halos here, subhalo is a halo that's fallen within the virial radius. So the big inputs that we need in order to do this is, aside from needing ourselves the high resolution n-body simulation, we also need an input stellar mass function. So that's an input. We have to get, so for our particular case, we draw the same stellar mass function that we obtain from our volume limited sample so that everything is self-consistent. The other thing you have to decide is how you're going to associate your galaxies with your dark matter halos. In principle, you can just say, put the most massive galaxy in the most massive halo, basic principle of abundance matching, and you're done. Unfortunately, it's not quite that easy, because in the case of these subhalos that come in, they tend to get stripped of their dark matter, and as a consequence, the mass is much lower, and so the galaxy at the center, which is not stripped very much upon accretion, at least immediately, will tend to have much higher stellar mass for its subhalo mass than you would expect. So as a consequence, you have to do something a little bit different. So input stellar mass function. But the question then becomes, what are you using for your abundance matching parameter? In our case, we end up finding that V-peak, what we're calling V-peak, is the best result. So rather than even using the mass, we're using taking the maximum circular velocity of the dark matter halo, tracing that out through the history of the halo, and taking the maximum that it ever was. Now this is very similar to the value for the present maximum circular velocity for isolated halos. But for subhalos, this is generally significantly higher and gives us the appropriate boost in stellar mass for satellite galaxies. Okay. We also assume two other individual parameters. One is a scatter, since we expect a certain amount of stochasticity in galaxy formation. The other is essentially disruption parameters, so that your satellites don't hang around forever. Once the subhalo is down to too low a mass, we assume that the galaxy it contains is disrupted and lost. Okay. Ground results, this is Bolshoi again. The output we get looks a little bit something like this, where your galaxies are tracing the dark matter as you would expect. To give a more precise example of what our results look like, this is a 2-point correlation function. The black points are the measurements of the 2-point correlation function from the volume-limited Sloan that I mentioned earlier. The blue line is the 2-point correlation function from our best model. Okay? All right. So these two on the left, which are the higher stellar mass thresholds, are actually very good fits. On the furthest right, we're down to the lowest limit, to the bottom edge of what we're comparing to in Sloan. There's maybe a hint of, maybe a hint at the smaller scales that we're not getting enough substructure. But otherwise, this is really good. Similarly, we also compare the conditional stellar mass function. We do a group finding as if we were observing on both of essentially galaxies in groups in both the Sloan and the Bolshoi sham model. Okay, and we treat the Bolshoi model as if it were the observations. So this is all self-consistent. Again, the black points are the data, blue points are the model, and this is actually, again, this is a very, very good fit. And these are abundance matched in reverse to get an estimate of the dark matter host halo mass that you would expect they belong to. So you can see that both in sort of small cluster sized halos, as well as these lowest mass down to almost Milky Way size, down to approximately Milky Way size. We're getting a very good match here with the centrals. These peaks is the central, the brightest galaxy that you expect in your group. The rest are the satellites, and again, it's clear that we are getting most of the substructure right. And since those two things are what we use to constrain our parameters, the scatter and this disruption factor, we also check a few other measurements. Particularly, you'll note the satellite fraction here, the fraction of galaxies at any given luminosity that are assigned to be as a satellite as opposed to the central, is basically correct. Okay, and lastly, this is what our constraints look like. The mu cut is not quite so well constrained. It doesn't have as large an impact. But the scatter is actually very tightly constrained, mostly by the conditional stellar mass function. There's a significant amount of freedom if you use the 2-point correlation alone. But this is it. Okay, and the two darkest contours are the 1 and 2 sigma. Okay, so just to throw the conclusions up here, basically at least down to around 10 to the 10 stellar masses, abundance matching is simple, accurate. It works, but only if you use this V-peak for the abundance matching. And that this measure of the depth of the potential well is the main driver of the galaxy properties. It also implies, based on this mu cut, that the halos are stripped significantly before infall, but the galaxies are not until significantly afterwards. So we expect this will be helpful in the long run for such future research as helping to constrain, particularly the low redshift semi-analytic models. And if you want more details, that's where you can find it. Thanks.